Whisky James Webb del Mercadona. No,
Y es barato, ¿eh?
Ahí para celebrar cuando dio un tiempo.
Ese te da una resaca.
Sí, es que la pipeline todavía no
Está bien calibrado.
no está bien calibrada. Okay, so I think that we can start. Thank you very much for being here. Today we have a seminar by our visitor, Antonio, which is leaving on Thursday.
Yes.
Okay. So he's from, you're from Madrid, right?
Well, basically, yes.
He studied in the Complutense, in the university. He did his master thesis there, and also for the project he worked in ESA.
Yes.
And he was working as a research associate in Siemens
Yes.
for a short period of time.
2 years.
And today he's going to talk us about dream emission like galaxies, but especially result, not like the ones from
So the good ones, right? So, hi everyone. So I'm starting my PhD studies right now. So I started on December with my supervisor that is José Manuel Biltzen and Ricardo Moritas is sitting over there. So yeah, I'm gonna start talking about this kind of galaxy, but first of all, let's introduce a bit the topic of the Reionization epoch. So let's start from the very beginning. In 1965, an astronomer called Smith published a paper with the discovery of this quasar, 3C9. So the importance of this discovery is that this was the first time that the Lyman alpha emission or the Lyman alpha photons were seen by human eyes. And right away, these two guys, Bryce Peterson and James Gunn, realized that what this is telling us is that the neutral hydrogen density in the intergalactic medium has to be really small between this quasar and us. And immediately, this discovery formulate question about how ionizes the intergalactic medium and where the ionizing photons come from. And this were a hot topic in astrophysics. So, but however, till 2001, when with the discovery of this quasar at 6.28 redshift, we didn't give a step further. And if we look to this plot on the left-hand side of the slide, we can see the fluxes of 4 quasars with the flux totally absorbed in the left of the Lyman alpha emission. So this was called the Gunn-Peterson effect, and it's telling us that the hydrogen fraction of neutral hydrogen fraction has to be larger than 10 to the minus 4. So now the big picture that we have is this summary in this plot of Fan et al. 2006. So in the x-axis we have the redshift, and in the vertical axis we have the neutral fraction of hydrogen. So we're going to follow this blue line, that is a model of 2003, I think, if I remember correctly. And we're starting an epoch where the neutral fraction of hydrogen is 1, and then start slowly to decrease due to, or driven by, the population star 3 of. Followed with this phase, we enter in a recombination of the universe with largely neutral, except for some isolated H2 region produced by individual ionizing sources. Then we enter in the reionization epoch until now. This line can be constrained with some observation. For example, the galaxy with the Gunn-Peterson effect that I mentioned before, the Strogen sphere, Lyman alpha galaxies, the measurement of the W map, and the last one was done by Planck collaboration 2020 that infer a midpoint right here, with we can reach the half neutral fraction of hydrogen at a redshift of 7.8. Okay, so this is the state of the reionization epoch, but who drives the reionization epoch? So we have two candidates, and one is in one hand we have the less luminous galaxy, dwarf galaxy, compact galaxies that have less gravitational potential, that favor stellar winds, supernova explosion, and this means that more Lyman continuous photons can escape from the galaxy. On the other hand, we have the brighter and the bigger galaxy. This galaxy has big gas reservoir of star forming and more gravitational potential. So if we mix these two facts, we get with this assumption that this galaxy are going to produce more Lyman alpha continuum photons, but it's more difficult to escape because they have less surprise feedback. So we can summarize these two populations with this factor, that is the escape fraction of Lyman alpha continuum, and say that this number has to be higher for less luminous galaxies, for dwarf galaxy, compact galaxies, and lower for the bright and bigger galaxies. So this number can be linked with this formula. In the green box, we have the total number of Lyman alpha continuum photon emitted by galaxies that came from stimulation, and this number is equal to these three factors. We have the escape fraction, we have the number of ionizing photons produced by galaxy, and the density of star formation rate. That is basically the number of galaxies. So we have the ionizing photons per galaxy times the number of galaxies times the fraction of photons that can escape from the galaxy. Okay, so this is our observables, and in concrete, this factor over there, that is number of galaxies, is basically the luminosity function in the ultraviolet. So in this plot of OM21, we have in the x-axis the magnitude in ultraviolet, and vertical axis the number of galaxies per magnitude per cubic megaparsec. And each line corresponds to one luminosity function at a specific redshift, starting at the upper part from redshift equal to 2 and going down until redshift equal to 10. And if we focus on this plot, what we see is that this point over there is indicating that at less bright galaxy, we can see that this point is moving. Okay? We have less, also the tail is shorter. So we can say that we have less bright galaxy when we move toward high redshift, and also the slope of this luminosity function is steeper. So combining these two things is telling us that maybe the candidate for the reionization are dwarf type galaxy, compact galaxy. So this is telling us that we have to point our instrument to compact galaxies. So this is totally observable, and now we're going to move to simulation, because simulation can help us to defend a bit on this topic. So Finkelstein in 19 did an awesome work on this topic, and well, let's focus first on the plot on the left. We have the different colors represented. On red is the most luminous galaxy. Purple indicates well, on red are the more luminous galaxy and the less luminous galaxy on purple. Okay, and this plot is just how evolved the global escape fraction with redshift. And this horizontal line in black represents the minimum established for consider ionization. So it's the 5% of escape photons. So what we see is that at this galaxy, with magnitudes higher than -15, the responsible of the majority of the photons that can escape. And the most luminous galaxy cannot achieve this minimum. So this is telling us the same thing. We have compact galaxy with feedback that open channel from the photon to escape, and this is telling us that this is true, that compact galaxy has more fraction of escape photon. And in the plot on the right is just the ionizing photon, that we see that also less luminous galaxy has more ionizing photon. So moving now to hydrodynamical simulation, point out in the same direction. This is a simulation of a dwarf galaxy. So the color represents the fraction of well, the density fraction. Well, no, it's just the density of hydrogen. And I don't know if you can see it, but there are some filament going from the inner part to the outer part, and that represents the supernova outflow. And this plot is linked. Well, this is from Trevitz et al. 2017, and this is linked with this plot over there that is quite nice. Well, is this the time scale on the x-axis and variation of mass, and this is the important axis that is the escape fraction. Okay, so in blue we have the star formation rate, in orange is the outflow rate, and the escape fraction is in red. And we can see that here that this is so beautiful that the outflow rate of this galaxy correlate with the escape fraction of photon. So this is the same thing as before. We have feedback in less luminous galaxy, in compact galaxy, that allow the photon to escape from the galaxy, the ionization photon to escape from the galaxy, opening channel. So yeah, this is basically all the theory that I know, because I'm starting the PhD, and this is everything that I know in these 2 weeks. But there are some open questions to this problem, and one of these is the role of quasar and AGN. AGN are a dominant component in this process, subdominant component, we don't know yet. Also, the feedback implication, the radiation pressure, outflow, supernova explosion, winds from the young massive stars, we don't know yet. But for example, in this simulation of Castellanos 16, we see two, well, the colors are the density of hydrogen. We see these two pairs of Lyman alpha emitters that are opening channel to the rest of emitters. And the photon of these emitters that are outside is the one that are escaping from the galaxy. So this is the message of the theory that is now on the field. So these are the questions, but we have problem, and the big problem is the transmission of the medium. At high redshift, we cannot observe this photon directly, even with the James Webb telescope. So for us, it's impossible to have measure of this kind of object. So the solution is moving to local redshift and find local analogues. So this is the theory. Now we're going to study in details galaxy. In concrete, is local analogues. But what is a local analog? Well, high redshift galaxies are basically characterized as these four features: are strongly star-forming, as metal poor, increasingly compact, and it has other radiation fields. And these properties are sharing with green P galaxy. So the beautiful of green P galaxy is that this green P galaxy at redshift 0.3 or 0.4 has escape fraction from the 5% to the 75%. So this is something quite interesting to study. And this is some observation of 5 green P galaxies that we have observed. Are characterized by with a huge emission in oxygen 3 with equivalent width larger than 200 or 300. Also the emission in ultraviolet because are star-forming galaxy. And these are the profile of the Lyman alpha emission of these 5 galaxies. Okay, so in the literature, we can find a bunch of this kind of galaxy, and this is an example of isotope 18. This plot in the left is just the Lyman alpha line, and we see that we have a blue and a red component. And these two plots over there are the full ultraviolet spectrum. And if we zoom in to that region, we can see this point is the Lyman alpha continuum emission. So it's not zero. We can detect it in this kind of galaxy. And this is so interesting. Okay, so, well, we have local analogues, and we have a problem of detecting Lyman alpha continuum emission. So we're going to try to link the escape fraction of this local analog object with the kinematic of the ionizing gas. So in the paper published by Amorim 24, we see this different line profile of these 5 galaxies, and we observe that they have complex gas kinematics. So we see that they are not Gaussian. I mean, are Gaussian, but totally asymmetric with more components. So it's totally chaotic. And this can be a signature of stellar feedback or turbulence in gas. So we can see that narrow components, for example, the red one, are components driven by star-forming clamps, and broad emission with velocity dispersion greater than 100 km per second are due to outflow. So if we assume that, we can go study this kind of galaxy, study the kinematic of the gas, and find the channels or the mechanism for photons to escape from the galaxy. So I'm working on it with a data sample of only, by now, 4 galaxies at a redshift of 0.3, 0.4, with escape fraction from 2 to 70%. This is the description of the sample with stellar mass of 10 to the 9, highest star forming, and subsolar metallicities. And these 3 pictures are the galaxy. Well, I have 4, but I only find 3 of them. And we can see a feature that is really interesting. That is that we have some. This is the compact core, and we have some burst or something we don't know yet. Companion maybe we don't know that is present in the 3 candidates. So these images are taken with the with code with HT. Now from the rest of the talk, well, for the rest of this section, the result that I want to present are basically of this galaxy J1154. So remember this picture that we have this core, and here we have a cloud or a starburst. We don't know yet a burst there. Okay. But now this data we're taking with Megara. This is for example, if someone has interest in Megara. Megara is an IFU spectrograph with a field of view of 12.6 arc-second times 11 arc-second. And this is not a problem for us because we have compact sources, so it's perfectly fine. We are going to observe extended sources. Also, the spatial size is 0.62 arc-second and allow these 3 resolutions, 5,000, 12,000, and 20,000. In our case, we have the lower resolution, but it's totally enough for us. And this is all the band that Megara allows to observe. So yeah, going through the methodology, one data cubes has 40 times 43 spaxel, and that means that we have 1,720 spectra, and that's a lot. So this is so time consuming, and we have to address all this problem of dealing with big data and so on. So just after running the code of the Megara pipeline reduction, we have to estimate the uncertainty per pixel in the spectrum. And this is something that the Megara pipeline doesn't have. So we have to use this tool developed by Cabello 24 that consists basically in adding Gaussian noise to each of the calibration images and object images and run the full reduction of the data cube. And we repeat this process n number of times, for example, 100 times. So at the end of this process, we have the original data cube and 100 data cube with Gaussian noise added to each pixel, to each image. Okay, so we can take the standard deviation of each data cube and calculate and compute the error spectrum of each of the 1,720 spectra. And this is what we get. This is only one pixel, one pixel of this data cube, and we have the emission of oxygen 3, H beta, and so on. And in blue, we have the error spectrum. Okay. So this is so time consuming for 15 data cube, one day. So, okay. So later, what we have to do is to fit and try to subtract the continuum. And for doing that, I like to work always with Bayesian analysis, and this is what I did. I try to fit the continuum of this is an example with one spaxel. I try to fit the continuum using the MC code. Okay, and I like it because I can get the posterior, the probability of one parameter to be in one confidence interval, and I mean, I think this is worth it. So this is the result. Is almost zero. Is it what it is? Is zero. Okay. So with the continuum, we can subtract the continuum to the original data cube and obtain a data cube only with the line emission of the spectrum. And if we focus to the oxygen-3 emission, this is the spatial distribution of this galaxy in oxygen-3. It's just a ball. We don't have enough spatial resolution to achieve to see the inner structure of this galaxy. But we have the kinematics. We can go to the kinematic space and try to resolve the inner structure of this galaxy. And this is the powerful of this method. So moving to the kinematic space, we have to fit 1, 2, 3, whatever Gaussian to each a line profile, in this case oxygen-3, we're working with oxygen-3, and also with Bayesian analysis. Well, we feed 1 to Gaussian, and we take the velocity dispersion, and amplitude of its component. Okay, and this is the result. So this is only with one component, and in the plot on the upper part in the left, we see a clear velocity map rotation, but the interest is on this bump over there that can be correlated with this. So maybe it can be correlated with it. And also we have this corner with some more components to the blue, to the red, and also the velocity dispersion is higher in this region. So this can be correlated with this band. But also this image was taken with the HT in the near ultraviolet. Well, this image is horrible and we cannot see because of the contrast, but anyway, it's supposed to be a point here. And this image was taken with the HST in the narrow band with a width, narrow band 680, I think, 680. Yes. So we have claims that something is over there and is emitting in ultraviolet and in oxygen-3. Okay, let's go to the two-component analysis. And these are the results. The upper part, the first component, and the second, and the lower part is the second component. And what we recover with the first component is that we have velocities. Well, this is not too much important. The important part is the velocity dispersion that are 60 kilometers per second, 80 kilometers per second, that are mostly the same that we achieve in the one component. So this is something that makes sense. But if we go to the second component, we start to see things. We have this band, we have this corner, we also have in velocity dispersion this one, and in this region, in the upper part. And this component looks, the scale, goes around 130 kilometers per second. And we said before that high velocity dispersion can correlate with outflow. And this could be the mechanism for a photon to escape from the galaxy. So this is something that we are working on it. I think it's promising and it's so beautiful. Try to find the way that the photon can escape from this galaxy using kinematic analysis, using how the gas velocity is in this galaxy. Okay, so going now for the last section of this seminar, I'm talking about theory. I talk about the time study of one galaxy. And now we are going to move to a more statistical studies. So a statistical study nowadays means thesis, the dark energy spectroscopy instrument that has observed 1 million of the galaxy and quasar. But this is only the 2% of the full dataset that DESI will release in the future. So what is the goal? Well, we aim to search for this green pea galaxy and for these Lyman alpha emitters. And this is a spectrum of how we can see this green pea galaxy on DESI with high emission of oxygen 3 and so on. So, first of all, we have to create an example of the DESI catalog. And for creating the example, what we did is to use this clustering machine learning algorithm called k-means. So really quickly, what k-mean does is we have a set of data point with some dispersion, and we can, well, we initialize 2 centroids, for example, or 3 centroids, whatever. We initialize 2 points and compute distance between each point in the dataset to the centroid, and assign a centroid to each data point based on the distance. It is shorter or longer the distance, assign a different centroid. So we train this kind of algorithms with a sample of the DESI catalog from redshift 0 to 0.25, and these are the results. We can distinguish 3 different classes in this result. First of all, we have the outlier classes that are the galaxies that don't have any Balmer absorption line. Also, we have, well, these are, we cannot see the Balmer absorption line here, but anyway, trust me. But also, we have this plot that in red highlights the minor classes, that is just the 1% of the sample, and the rest are the rest, okay? So we can see that in the 1% of the sample are this kind of spectrum with high emission lines. Okay, so we have this algorithm trained, and we take the centroid and apply to the full DESI catalog and make the classification in the full DESI catalog. And once we have the sample ready to work with it, we have to measure. And for measuring, we have this fantastic tool from Vital that is called Lyman. Lyman is a powerful tool that allows us to compute line fluxes, amplitude, also has signal to noise mask, everything. You can do everything with it. And the good point, or the best point, is that is super fast. Super fast. We can run 50,000 of galaxies in less than 1 hour, feeding all this line. So it's so powerful. And also the plot for visualize everything is quite nice. So with this tool, we measure the DESI catalog, and this is one of the results. This 3 color, well, this plot is just a BBT diagram, is the nitrogen 2 over H alpha and the oxygen 3 over H beta. And we have 3 different colors that correspond to, in green are the outlier class, in blue are the major class that I didn't define before, but are the classes that are follow the minor classes are these 2 1, okay, 10 and 11. These are called for us a major class. And in red, we have the minor class. So we can see that this is the data point that we have, the spectrum that we have. And for example, these are two different spectrum. This point over there is an AGN with a huge emission line galaxy, but also with a emission line galaxy of excitation, of high excitation, like a neon 5, and broad component. It's quite small, but there are broad components in nitrogen 2 and oxygen 3 also are broad. Also, the outlier are extremely emission object. Look, we cannot see the continuum and the emission of oxygen 3 and other lines are huge. And just this red point is a classical star formation galaxy spectrum. So this is also work in progress. Ricardo produced this plot 2 days ago, I think. So it's work really work in progress. And for for finish this seminar, I want to establish a connection between this work, the work that we are doing with DESI and JPass. The idea is to, okay, we have this sample of 20K galaxy, 20K emitter galaxy, and what can we do is create a synthetic photometry combined with a filter of JPass and create a sample for knowing how this object looks like in JPass. And if we do that, this is a plot taken from Iglesias Paramount 22. This is how this look like. They are compact sources with high oxygen 3 emission and the H alpha over there. So the goal is to create a big statistical sample over the 5,500 square degree of sky with JPass. So this is gonna be the future. So for summary, everything, we have that green pea galaxy has a very complex ionizing gas kinematic, and multi-component Gaussian analysis is quite important for trying to resolve these galaxies. Also, the high resolution IFU data will help, obviously. We have created a sample of 20K objects derived from DESI, and with JPass it could be possible to find more performance statistical analysis, looking for companion, state environment of these galaxies, and so on. So this is something very important for the future, and we are gonna go in that direction. And finally, I want to say something for the Spanish speaker, is that I have a podcast called 5 Sigma, and we can find it in, well, no promotion. But you can find it in Spotify and YouTube. This is the first chapter, and we interview Otero Santos, that is an astrophysicist working in CTI in gamma rays. Well, and the podcast is done by me, Alberto Pérez Torres, and Javier Méndez Gallego. And just to say thanks to everyone, to Daniel, say thanks for everyone for going out and having dinner with me, to Ricardo with the asado, and for being the best supervisor as possible. And thank you also to Juan to give me the opportunity to give this seminar and the FECA team. So thank you.
Thank you very much, Antonio, for the very nice talk. So now questions. Sepide?
I have a very basic question. In Lyman alpha green pea galaxy, you show some green pea galaxy had the Lyman alpha had 1 peak, while the other had 2 peak. Why?
One, right?
Yeah.
I think it depends on how we see the rotation of the galaxy. No? You have one component and one red and blue component.
Yeah, it also depends on the geometry and the covering fraction of each one. So basically, if you see the blue part of the line in the line of sight you are observing, you are seeing the Lyman alpha photons escape in your direction. That's the part that is more easily absorbed by the H1 and the dust in the line of sight. And instead, the red part is since this is a resonant line, is the product of the scattering of these Lyman alpha photons in the medium. So that's why it's broad. So basically, bottom line, if you see the blue peak, then is and the blue and the red peaks are close, then you see a smaller covering fraction of H1, therefore a larger phase fraction.
Thanks. Thank you.
Continuing with the basic questions, in your slide 11, you said that the star formation rate correlates with the effect on escape, and you showed these two examples. But if we see the curves, we see that this is actually not what happened in most of the cases. So
Well,
What caused that, for example, in 6.1 at sea, it correlates very well, but 6.7, no.
well, it's also correlated. Look, this peak and this one.
But the scale is.
The scale is different, but it's correlated. Well, we don't know the effect that are happening in the
So
galaxy.
what affects the scale of one of another, or doesn't have anything to do with?
I don't think that the relative scale between these two components has to be important. I think that the important thing is that we see that there is a peak of outflow that correlates with a more escape fraction. I think that is the point of how bigger and how smaller it is.
I see. What happened in
And also the scale is different. We see this scale is from 0 to 1 and this one is from 0 to 4 in a different unit also.
And what happened in 8.4? We see a peak in the spectroscope and a valley in the mass formation, the star formation rate.
Yeah, that's true. But what this happens is that you can have an outflow that can clear the dust of the environment, and that's it. And then the second burst of ionizing photon can escape. Has not to be immediately correlated. But in this case happened, but not there. We don't know the geometry of the galaxy also. So they are important factors.
Yeah, that this is a simulation, a nice simulation, hydro simulation, but it strongly depends on the feedback prescriptions. If you see there is a delay between the star formation and the outflow, so there is a delayed effect of the feedback in the stellar medium. And as Antonio said, I think it's also dependent on the geometry, on the dust distribution. So it depends on what is your dust production after the burst, and then the distribution of this dust in the different lines of sight that you are covering. What I mean is that escape fraction is not only dependent on outflow and star formation rate. It's also strongly dependent on geometry and how these interstellar medium conditions are shaped. Yeah, that's the point. But this is an indication. Outflow should clear out the dust, so the elements that block yeah.
More questions? Kasu? Yeah, concerning the k-means clustering. Yeah. So what are your input variables for the k-means? Because then afterwards you saw the BPT diagram and it looks like the clusters are not very well separated.
Yeah, I didn't mention, but the input are this window that we have in gray color. Are centered in the most important feature of the galaxy. For example, oxygen 3, H beta, nitrogen H alpha, and oxygen 2. And I didn't do this k-means, but I think that they just put these windows and introduce the value of the fluxes in these windows.
Yeah, we initialized the clustering algorithm only with this limited sampling ratio, just to have all the relevant emission lines in these windows. And to reduce the number of elements.
So more or less are the 8 windows that you have in gray.
Exactly.
So 8 parameters.
Exactly.
Okay.
Well, not parameter. I think I add the fluxes, right? It's just
no, we consider pixel by pixel, yeah. So it's more than 4,000.
It's a short spectrum.
Yeah, okay. It's a
short spectrum.
Yeah.
Because we don't care about this region that is totally empty. Like we have to introduce that.
Perhaps some details. So after the initialization. We define these centroids. These are the centroids of each cluster. The number in parentheses are the total number of spectra of each centroid. And the ones between ask 0 and 11 contains 99% of the total sample. So these were called major.
The major
classes. Yes. And then the 1% remaining are minor classes, which are the 3 in red. And the outliers are those we cannot be assigned to any other cluster. And you can see the numbers are very, very small. This, of course, strongly depends on the number of clusters that you want to create. But an important point of this work is that we are not aiming to classify spectroscopically DESI. What we aim is to use k-means as a filter to get
to select.
everything which is not normal spectra. So the important ones are the outliers. But of course, there is a continuum of spectra, and since this is the case of the minor classes and the last two major classes over there. So we didn't show it, but we have used the value-added catalogs to check whether these galaxies belonging to these centroids have the properties or equivalent widths, etc. And we validate this method.
It's like a pre-selection method.
It's a pre-selection. Instead of measuring the whole DESI database, we just focus on the 20K minor classes or spectra that looks like what we want to analyze.
Yes. Thank you for your talk. I wanted to ask about the green pea galaxies that you are starting to analyze with the Megara data. Why those 3 or 14? Are those that have companions? What is your hypothesis for the why does the companion matter? What does it do, etc., etc.?
We don't have any hint about companions, but the important feature of this galaxy is, well, we have the hint out with the, what is it? But we have the hint of this, but I don't think it's the property, the key property for studying galaxy. The property is that has an escape fraction from 2 to 70%. So this is the property, and this is why we want to study this galaxy. And using Megara data to see the kinematic of the gas and try to resolve and find the channel of the photons and so on. I think this is the property. Also has a huge equivalent width in oxygen 3 and can correlate in some aspect with the fractions.
That doesn't impress me that much.
These were the first strong Lyman continuum meters that were detected by Isotope. So that one is one of the stronger ones with 64 or something like that.
No, this one has a 70.
That one
Whatever.
has 70 something. Yes.
So I'm curious, why didn't you take the Megara of the first one?
Sorry.
Do you have Megara?
Yes, I have.
We have.
Okay.
He still didn't show it because he's still in the
Because
process.
that should have been more impressive, right?
Yeah.
But also it's more complex.
Yeah.
So first I need to develop the skill for analyzing the data cube, and then I enter in this game.
Exactly. So I'm also curious. So the first part of the talk was about Lyman alpha, and then you came into the green peas with O3. About the connection between Lyman alpha and O3. I was trying to review my previous studied papers, but I couldn't at the top of my head find a plot that shows how Lyman alpha correlates with O3. Has there been? There must have been some good papers on this. What's the general trend?
Yeah, this is something that I discussed with Ricardo just a few hours ago. So yes, there is an indication that the equivalent width of oxygen 3 correlate with the fraction of escape of the Lyman alpha. So we have seen that a galaxy with high escape fraction of the Lyman alpha continuum photon has high equivalent width in oxygen 3. But in the opposite direction, it doesn't work. So the relation is not clear at all. But this means that oxygen 3 is an indication of star forming, for instance, star forming, and that creates ionizing photon. It's a signal that this galaxy is creating ionizing photon. So this is the connection, I think.
Yeah, well, basically the equivalent width of oxygen 3 correlates quite well with the Lyman continuum photon production.
Okay.
Because basically the equivalent width tells you about the age of the younger star population. So the younger the massive stars, more photons they produce, and this declines very sharp very, very rapidly. But the escape fraction, so you can have very strong, very high equivalent widths and very high escape fractions, but the other way around is not necessarily true. So you may have very strong equivalent widths, but without any. 1Wiki18 is one example, for instance.
Sorry?
1Wiki18
Yes.
is one example.
Mhm.
Because this strongly depends on the neutral gas, the H1. If you have a covering fraction, so if the galaxy is entirely covered by an optically thick layer of H1,
then
you can produce whatever you want, but you will
nothing's
not.
gonna come out. Exactly. Yeah.
Okay, questions?
I'm also curious if you have looked if any of your galaxies are active galaxies or something, because you want to look at how AGS can play a role in this, right?
Active galaxies, you mean with AGN?
AGN.
No, I didn't look, but in the spectra, we can see that there are no broad component and highly ionized lines. So, at least in this galaxy, no. The other one, I didn't see the spectra. So,
In general, we don't have any strong indications of AGNs, at least based on classic diagnostics. No X-ray at all. No very high ionization lines like in
Yeah, if you show the VPT slide,
you can see the slide.
you can see that the galaxy up on the right, it has strong neon 5 lines. Neon 5 is high ionization line, and you need a stronger continuum, a steeper continuum, like the one from the AGN to produce such a high ionization species. If you don't find those lines on the other spectrum, then that means that you produce a lot of oxygen 3, but you cannot reach higher levels of ionization. So that helps you to figure out if there is an accreting black hole or not.
But of course, you can expect that objects like those with very high ionization can also produce Lyman continuum photons, and some of them will escape. But that's not the case for the big.
Question: what do you plan to do now? Do you plan to focus more on the Megara data for resolve studies or on the statistical?
this is an easy question because I have a talk in SEA and I have to present the result of the Megara data. I have to analyze 3 more. So yeah, the main point is to focus on this analysis.
So after July, you do the statistics. No?
Yeah.
Just related with that, I also have a question. So you didn't mention anything about your statistical approach after the k-means. What should we do with the k-means output?
Yeah, we have this. What? I think we have this big sample of 20K object, and what we plan to do is to use more sophisticated algorithm, deep learning algorithm, to try to find this kind of object in the future DESI data release. So this algorithm that is called a contrastive machine learning is faster, and we hope that this will be better than use k-means that use k-means in a big sample. So the plan is to use more sophisticated algorithms using deep learning techniques, trying to reduce time computation and so on to find this object in a massive way.
I think it's important to mention that because here we have Jesus.
I was going to suggest that
Yes,
doing an unsupervised approach, then you can do k-means or whatever on the representations that you take from contrastive learning. So that would be a nice way to do it.
I think we have a lot of room for collaboration, especially thinking to learn something about how to deal with the JPass data in the future. So perhaps doing this with DESI, we can learn about how to look for the photospectra correctly in thesis and try to use this kind of tools to classify and
Yeah, and to find more candidates or candidates in an easiest way. In an easier way. Yeah, that's good. Don't hesitate to talk to me or Elena. So good at that. But yeah, it would be a nice way to find more candidates and also to look for some indications far apart from the oxygen 3 that can be more but that can constrain better the different candidates. So yeah, that's a good way.
Okay. Any other
I
question?
have an anecdote on the discovery of reionization. Because you showed this paper from 1965 at the beginning. And 2 years ago, I gave a talk on the discovery of quasars. Because there was a Star Trek episode from the 60s that mentioned the quasars, but we didn't know what they were yet. So they mentioned some things that were already discovered, but there were many things that we didn't know. So I started reading a lot of papers from the 60s on quasars. There was this debate, like there are objects really far away with unimaginable amounts of energy coming out from a mechanism that is unexplained, or there are smaller objects closer away and maybe going far away at high speeds, and that explains the redshift. So one of the things they did is like, okay, if they are very far away, hydrogen in the universe will absorb the light coming from them. So they did the measurement, and they're like, okay, we don't see this absorption, which means either the universe has barely any hydrogen, which conflicts with everything we know about it, or most of the hydrogen in the universe is ionized. So now you have to explain that, which is an absurd thing. So they have discovered the reionization of the universe, and they were like, no, how can the entire amount of hydrogen in the universe be ionized? Now we need another huge energy thing to explain this. So they were arguing, this means this quasars must be nearby close, small objects that don't emit that much energy. So I was like, what the hell? They had discovered reionization.
It was the most logical conclusion.
It was the less outrageous interpretation. Like, how can you ionize the entire amount of hydrogen?
As long as you leave the discussion written, it can be useful afterwards.
When was that paper? This paper?
In the 60s, it's like, I don't know.
A couple of years before 65, or
It could be because I don't remember the exact year now. Because I was reading not only papers but science popularization articles of the era, because those are most likely to have been read by the scriptwriters of the episode.
yeah.
So there were some articles in magazines explaining the 2 points of view of with Newton. So I think it was in a paper, right?
Smith was the first one, right? So probably.
Yeah. But some of the measurements were done in order to distinguish whether quasars were nearby or not. So it's like, okay, we don't find all this absorption of neutral hydrogen, which means there's either barely any hydrogen or it's all ionized. Like how is it ionized? So it's like, you're so close to the discovery, but they weren't there yet. So maybe this was a bit after that.
I was reading a science popularization article from the 90s, muy interesante, that my father had when I was a child. And there was an interview with Margaret Burbridge.
Oh, yes.
Who still believed quasars were not in the 90s.
Yeah. But now we see like, in this year they discovered this, and in this year they discovered this. Right? These are the clues that lead us to believe this. But in that era, there was so much debate.
Exactly.
We just get
the one that were right.
The cherry picking, the things that they got right.
Halton Arp, the one that gives the name to the
Weird
interacting galaxy, he thinks that the quasars are not, that the redshift interpretation of quasars is not correct. And he has like an Astro PH submitted in early 2000s about the abnormal density of quasars around some nearby galaxies. Like he was suggesting it was something related to the halo or something like that, rather than something far away.
Because they had discovered radio galaxies already, but quasars were like several orders of magnitude higher in energy, and they didn't know about black holes yet. So they thought maybe quasars are I think it was Centaurus A, like this closer radio galaxy. Maybe
yeah.
that kind of explosion of energy at the center of that galaxy threw all these energetic objects away enough time ago that we all see that we see all of them reshifted, no blue shifted ones. So this is one of the kind of things that we're saying in the 60s. So yeah, that led to the reionization discovery because like, okay, let's see. There's hydrogen that would tell us they are really, really far away. And there wasn't.
Then in 73 was the paper by Sakura and Suya about the accretion disk, and then after that they identified the accretion of matter as the powering mechanism.
They didn't know yet. They're like, what is going on?
Okay, one last comment to finish. This is going to be useful for the students in the room. You come to Lumbrera's house and you don't cite Lumbreras in the...
Wow.
So take that into account whenever you give a talk or a seminar elsewhere to look first who is in the room because your intros and the citations in your intros depend on that. Otherwise, he will call 500 policemen at the main entrance.
That's why they were there.
Any last comment?
No, I think I can go now.
Okay, so let's thank again the speaker. Thank you very much. You're dismissed.
Es verdad que sí.